for disjoint sets where we will show you some codes. Okay, so during the class I may not discuss too much about the codes, but tutorial will be about the codes for disjoint sets. We will also discuss the last year's assignment and what are the codes you should use for that. Okay. So let's start from where we left yesterday. So remember we were trying to see the implementation view of disjoint set ADT, right? We talked about disjoint set ADT. And we tried, and we took an algorithm to understand the implementation view, how efficient that will be. We took an algorithm that required OM make set, OM find, OM sorry, OM make set, OM find, and O of N union. So this is all we needed for the algorithm. And we said, okay, I can do using an array, but that came out to be roughly order n plus n square, right? Using an array, order n plus n square. And now we are searching for an implementation that will be better than that. And that's where we got the idea of linked list. Okay. So in linked list, we said, fine, we will denote each set as a linked list. Now, how would make set happen? So I realized yesterday while talking about make set, I made a mistake. Anybody can tell what was the mistake I made in make set? There was a mistake in make set. And I think that might have confused you also. So I'll first, correct that mistake. So, so make set, I said, fine, I'll do make set. In make set, what I need to do, for each element, I have to make a separate linked list. Okay. So for that, I showed this picture, that this is how I will make a make set. But here I have two nodes. I have two nodes in my linked list. So I need to have only one node. Okay. So what is the mistake here? So it should have been, okay, I'll just erase this part. So you have this is your head pointer, right? This is the head node. This is the head node of your linked list. And yeah, this anyway is the next pointer. So you have the next pointer. So actually you only have an ID or a value, right? I'm only making use of an index. So that index comes here. Yes, so that I can even write inside. That is the ID. Yes. And and we have a third element that we will use for back pointer as we saw. So right now this will point to itself. This can point to itself. And this is sufficient for make set. Okay. So you will do it for all n elements. All n elements. You will create this. And somebody asked yesterday whether we will store head pointers in an array. I said, no, we don't need that. We only need to store addresses to all these. But now head pointers are the addresses of all these nodes. So I just need to store that, right? So I need an array where for each element I'm storing the head pointer for each element. Okay. So this pointer, that's what I'm storing for all the elements.
Sir,
Yes.
so could you please unshare and reshare your screen because I cannot see the screen that you're sharing. So
Oh,
maybe it will be visible after.
okay. Can you see that now?
Yes, sir, visible.
So now for each element, I am storing a head pointer. Okay, and that gives me a direct access to that element. Yes, I need this address to access this element. So this was a mistake. Yes, so this here I'm correcting that, and I need to store this. I was saying store the address, that is nothing but the head pointer. That will give you the address. Now I need to store some other things, and we will see based on our requirement what else I need to store. So fine. Okay. Now let's take a general scenario. What would happen? You have
Sir,
two. Yes.
do we store the address of head pointer of the ID, or do we store the address of its node itself? Sir, am I audible?
Address of the node, right? The value of the head pointer.
No, sir. If the head ID of 1, 2, 3 is same, then the linked list starting with ID some X will contain 1, 2, 3, right?
There is some. Let me just use some X. General X. Here. Okay. So
Yes.
you are storing this address. You are storing this address in the array. Address to the node.
So, sir, which the elements which has this ID will store the same address?
Yes. And this address you will not change. You will not change this address. Okay.
Okay.
So this is the address to the node, right? Now, uh, in general scenario, what will happen? You will have some linked list. Suppose you have these two linked lists. Okay. So you have the head pointer and this pointing to the head. Now, what we are saying, the head node will store the ID. So that means whatever the value of head node is there, that is the ID of the entire set. Yes. So now all of the nodes will have a back pointer that will point to this head node. That is all right. Now, if you want, you can also complete it by saying yes, this back pointer will point to itself, like it was doing earlier.
Sir, if we're directly storing the address of head node, then do we need to doubly linked list?
What do you mean? Why do you double linked list?
Sir, we will need, because after taking union, how will we access ID?
That I will tell. That I will
Because
tell.
without that pointer, how will we access if we don't have back pointer? Because we just have the address of each node.
Yes.
So if we don't have a back pointer, then how will we access the ID of the set to which that node belongs after taking some unions?
No, no. What is the question? Back pointer we are storing. Back pointers we are storing.
Sir, in the array we are storing the address of head, right?
Yes.
Then, and again in the doubly linked list we are.
Array we are storing head or the nodes?
The address of the nodes we are storing in the array, right?
Yes.
So you said heads.
Okay. Yeah. So yeah. Given a node, you need a way to access that, right? And the head pointer gives you a way to access that node. And that is what we are storing. That is what we are storing. So let's see what happens in union, and you tell me where the difficulty is. So what will happen in
Sir?
union? Yes.
Sir, can you please explain this with an example? Then I think it will be clear. I mean, I'm still having some doubts.
Sure. Let's take an example. Let's put some values. Three, 2, 10, 5, 7, 9, 1, let's say. Okay, so what I'm saying, in each linked list, the head node that stores the ID of this set, and all other nodes, they have a back pointer that will point to this node. Okay, now for each node you already have, when you did the make set, you know the address of this node, right? So that you are storing, that was the original head pointer, yes, that you are storing. Now what is good about it, now you also know for each linked list what is this address, what is this, uh, uh, because you already, for this 3 you already have it here. For 3, what is this star HD, that you are not going to change, and that you have here. Okay, so you have the head for each of the linked list by this array. That is what I want to convey. Okay,
So 3 is also one of the element.
will
3 is also one of the element.
is also one of the nodes. Yeah, that's what I said. In makes it, I corrected that. I said yes, this is actually a node. So even the head is actually a node that stores an actual ID or a value. Okay, so this is an actual node. And the head node, whatever the value is, that is the ID of the set.
And in the array, at the element to which address will be stored? Can I confirm?
Yes. Initially, when you did make set, you created a pointer to the node, right? The head for each linked list. That is the address you will store here. That is the address you are storing here. And that is sufficient to access each element. That is what I'm saying.
So sir, then the back pointer is not necessary, I guess.
Can the
Pointer to the head, the back pointer.
see, you may do without that also, but that is not, I mean, that will not be more efficient than this. So you will have to use some space at every node. So let's do it this way. That's what I'm saying.
So this is somewhat similar to the adjacency list type thing, like multiple linked lists going to.
So back pointer for each node, there's a back pointer to the head, right? So now this is your construction of the linked list. So you know make set is order 1 and find set is also order 1. Okay, find set, you just go to the node and follow the back pointer, gives you the ID. Now the question is what happens in union?
Sir, what is the array of, sir? Array contains heads or nodes, sir?
Array contains address to the
Sir, if it
node,
contains nodes, then
node. Okay, and that was the initial head pointer for all the nodes. Now what is interesting is that in this linked list, the way I will create it, for each linked list, the head pointer will not change. For this element, the first element, the head pointer will not change. So that means this will also serve you as the head pointer for each linked list throughout the operations. If you are at the head node, you have the address here. That's all I'm saying. So that means you have the head for all the linked list. You have the head pointer for all the linked list here. In this one.
So sir, actually initially we are storing only the addresses of the nodes, but which turns out to be heads of the linked list too.
Yes. What I'm saying, when I will do my operations for each linked list, this pointer, the head pointer for the pointer to the head node will never change. So throughout the operations for each linked list, you can find the head pointer here once you know this ID. Okay, that's all I'm saying.
Sir, how come find set is order 1? Because first we need to find the element in the linked list, so that will take order n.
last time we said, right? You have this mapping for the index. For each node, you're taking a very simple case, they are denoted by index. You have this array that gives you a pointer to that node. So if you want to find 9, you go to this array. This index will give you this address. Okay, now once you go to this node, you have this back pointer and you get the ID. So this is order 1.
Sir, make
Okay,
set
sir.
of order 1. So it should be like we are creating n nodes at first, so it should be order n.
What is order n? Make set is n make sets are order n.
Okay, we are calling make set n times.
Yeah, we are doing make set for n elements. So order 1 is each element. You will do n make set. Order n make sets. This will become order n now.
Okay, sir.
Each make set single set is order 1. Same here. Each find is order 1. If you do m finds, it will be order n. Okay. Any confusion in make set and find?
Sir, so at last we are only defining no heads or nothing. But the heads and nuts are same for something.
Yeah. Okay. Let's do union now. So what do I need to do in union? Union xy. So in union xy, I will have to union these two linked lists, right? So from x, wherever x is, wherever y is, I'll follow this and I'll find these IDs, right? And they will not be different. That's where I'm going to union. So if I'm going union, what do I need to do? How do I merge them into a single
Change
link?
the head ID.
I'm sorry?
Change the ID of head. Like for X it is 3, so turn the Y head ID of this to be 3 also.
What are you saying? So this, I'll do this.
Change the 5 means change this 5 into 3.
Are you saying this will, no, are you saying this?
No, sir, change back pointer to the head of the ID.
So you are saying 5 into 3.
No, sir. We should change the pointer.
No, this will not remain in the list if you do that.
No, sir. Sir, we can insert at the front of the second linked list. No, sir.
What you need to do, simple thing is that put one linked list at the tail of another.
Do I have to change all the heads, sir?
Oh, that's all you need to do. Yes, you need to do that. That is what will take time. Put one linked list at the tail of another. Okay.
But sir, doing only this step will not suffice, because if we put, then we need to change the back pointers as
Yes,
well. For
Yes, sir.
for
Back
that, what
pointers
you
also.
do? So suppose you take linked list A, put it at the tail of another linked list B. Okay, you are putting A at the tail of B. So what you need to do? Change back pointers for all the nodes in A. Okay, so let me just do what it will mean. So in this case, suppose you are putting this at the tail of this. Okay, so what will happen? So yes, so this next pointer will point to this node, and these are all fine, right? Now these back pointers, should start pointing here. Yeah. So
Sir, if we do this, how is it better our arrays? We are
yeah, that's
doing
what
the
we
same
will
process.
find out. That's how we'll find out. Is it better than arrays at all? Good question. So we change the back
Sir?
pointer. Yes.
So could we use another pointer to store the address of the tail? Otherwise, we have to traverse to the linked list to reach the
Yes,
tail.
good question. That's why I said, oh, I need some other things here. So I also need to store what is the tail. I also need to store the tail. Okay. And this will change. This will change. This will change. So right now, what is the tail? Currently, the tail for this was this, right? But now what would happen? The tail node will become this. Okay. So tail will change. This will change.
Sir, how will that improve complexity? Because we are anyways traversing one of the linked list. Then in BIGO notation, it will remain BIGO of n only.
Yes, very good
Like-
question. That's what we will find out. Yeah, all your questions are valid.
I didn't get the purpose of that.
All of you are feeling that this will be as bad as the array, right? And it looks so. And that's what I will say. So what is the complexity of union?
O of n.
Order of n. How many unions I have to do? I have to do n unions. So if I do that, so overall complexity is order m plus n square, no gain. And who will go for these linked lists when I can do with array? Yeah. Unless I want to practice pointers. Yeah. So yeah, so no point. Okay, no point. So why am I even talking about this? Why am I even talking about this? So then we say, okay, let's think what we can do better. Let's think what we can do better. What we can do better. So you see, suppose I have these two linked lists. Let's think. Let's try to make it slightly better. Suppose I have these two linked lists, this and this. Okay, this and this. Okay. Okay, I suppose your question was about tail pointer, and I guess by storing tail pointer, you directly know what is the tail pointer, right? Otherwise, you have to, given a node to find out tail pointer, you have to keep on following the next pointers. Yes. Other question was fine. We can do that. This will not increase the complexity. This will still remain O of m plus n square. Yes, both of these are correct. Right. Now we have to see how we can improve from O m plus n square to something better. So tell me what you will do. I have two linked lists. If I have a union, that means I have to put one linked list at the tail of another one. So what can I do to make it slightly better?
Append the smaller linked list to the larger.
Append the smaller list at the tail of longer list. Okay. So first, append the smaller list at the tail of longer. Okay, that also means you need to store the size. So third thing, size. Okay, you have to store head, tail, and size. And size will also change. Fine, if I have the size, I know this one is longer, this one is smaller. So what I will do, I will put this at the tail of this, right? And change the back pointers of all these nodes. Does that help me? So that means, yes, I have to update back pointers for the smaller list. Now question is, does that help? In the worst case, what would be the complexity? In the worst case, what can be the size of the smaller list?
Equal to the n by 2.
N by 2.
N by
The
2.
smaller list can have n by 2 elements. So this will still remain order n in the worst case. So where are we gaining?
And sir, how will we come to know about the length of the list? We have to check that also.
Size we are storing, right? We are storing. So initially we make set all lists will have size 1. As you keep on doing union, you take the size of 1, 2, just add an update. That's all. In union, you know the two IDs, right? You know the two IDs. So you also know their sizes. You just add these and update. That's all. So you will know this head, tail, and size. They will need very small update, right? That will not be. That is not a problem. Problem is that I'm not gaining anything. I'm still doing order in the worst case, right? That is still order n plus n square. Now what is the what is the way out? How will we improve it now? So then we say, okay, we are getting something, right? We are saying that.
Excuse me, sir.
Yes.
So can you explain the line worst case?
In the worst case, the smaller list can also have n by 2 elements, right? The smaller list can have n by 2 elements. So even if I put a smaller list at the tail of longer list, I have to update back pointers of all the elements of the smaller list. So that will means order n updates. That's what I meant. Is that okay?
Okay.
Now where are we getting? That's why we say, okay, let's look more deeply. So let's have a deeper look. Let's take a particular node.
So one thing is we won't do order in for all of the unions, right? Only the last union may be of order n.
Right.
When we start, the orders will be less.
We want to prove it formally. We want to show it formally. You see? So for a particular node, okay? And this is back pointer. Suppose the first time you update the back pointer. First time you for a given node, only for a one node you say. First time you update its back pointer. What is the size of the resultant linked list?
Set 2.
2.
It is equal to 2 because this will be in the smaller list. Yes. Now say second time you update that pointer. What is the size of the corresponding linked list? First time means it is now in the linked list of at least larger than 2. Yes. Now second time you update back pointer of any node. What is the size of the resultant linked list? It would be in a smaller linked list.
At least 4.
At least 4. And you keep on saying that. So third time to the power 3. So kth time to the power k. Okay. Wow. So that means for each node I can only update back pointer order log n, not more than that. For each node, I cannot do more than order log n update of the back pointer. Wow. So that means.
Sir?
Yes.
Sir, I didn't get this point. Means greater than equal to 4 the size of this.
Yeah. So you got the first point?
Yes, sir.
Right. Now, you see, first time update has happened. That means it is in a linked list. What is the size of that linked list? Minimum size of the linked list. First time.
1 and 1.
2, right?
Yes, sir.
Each time update has happened, that means it is in a linked list of size at least 2. Now you are doing second time. It is already in the linked list of size 2, and it would be in a smaller linked list. So when you do second time update, that means you are doing a merging and final linked list will be at least of size 4.
Yes, sir.
Right, that is that. Third time you do it is already in a linked list of size at least 4. It will be in a smaller linked list. So overall linked list size at least 8. And like that, kth time 2 to the power k. And we cannot go more than n. A linked list cannot be of size more than n. So that means for each node, I can only update that pointer order log n time. That means total back pointer updates order n log n, there are only n nodes. Wow. So that means that was the main complexity, right, in my union. So now that means order n unions, we take order n log n time. And that gives you complexity with linked list is order n plus n log n. Complexity with linked list. And here that's where we are gaining over average. And L.
Sir, can you explain that part again? Second time we union, it will be greater than 4.
First time you update, this becomes a part of the linked list that is of size at least 2. Do you agree?
What, sir?
First time you update the back pointer, it becomes a part of a linked list of size at least 2.
Yes, sir.
After updating, right? Second time you updating means first time has already happened. So that means it is already part of a linked list of size minimum 2. Yes?
Yes, sir.
Okay. And its update will happen only if it is part of the smaller linked list among the 2 linked lists where the union is happening.
Yes.
Yes. What will be the size of the final linked list after the backup, second back update? Minimum
Yes,
4?
again.
Okay.
So sir, we are assuming the one as the smallest, smaller than the other.
Even if they are equal, this still holds.
No sir, here what we are considering is the smaller. We are considering it. Right? We are assuming that here this one will be always
This
smaller.
will be smaller or equal. Even if it is equal, this still holds. Less than equal to.
If this is larger, then it will only be part of 3
This is
elements.
not larger. This is only smaller. You do update only for the linked list that is smaller. Smaller or equal, right? Smaller, I'll say smaller, because if they are same, you will have to define someone arbitrarily as smaller. This you will never do back pointer update for a linked list that has larger number of elements. That's what we said, right?
Yes, sir.
So this will always be smaller. Equal still all these holds if this is equal to the other linked list.
So we will also need to update the size. So won't it take order n again?
Right, to order n for n nodes. So this doesn't matter. We have already taken n log n, so another n does not matter. This was the main thing, this back pointer update. Other things were there, but you were doing that only order one time per union, right? So that will be another order n 10 plus n, and that's
Sir?
what, yeah. Yeah.
Sir, what is M here?
M is the number of edges.
Sir, so if the term
M5.
of if the term of M still exists in the complexity, sir, shouldn't it be still O of n square?
No. Depends on your graph. In your graph, you can have a dense graph. If you have a dense graph, yes, M is n square. But if you have a sparse graph, then the M is order n. Then M is order n, and then you are gaining. In all your complexities that you do in graphs, you always write separately for edges and nodes. Why? The reason is that the final complexity will depend on how your graph is. If it is dense, you say yes, edges are order n square. But if it is sparse, your edges are order n only. Or then accordingly you substitute and see what is the complexity.
So
Automatically, we
we
will
can
just set on
always
the
say
full
order
line.
of n square because it's
Yeah,
not
you
a
can
tight
say.
bound. We can obviously say, but
I know
I
that.
mean
I know
for
that.
tight bound we can
I know
use
that.
m.
I know that. Okay, I know that. We can always say m as n square. We can always write it as O n square. Yes, you're not wrong. You're not wrong. What I'm saying, that does not give you the realistic estimate, because many times, like in the next week, you will see problems about spanning tree where the number of edges in finally you will need are order of n. So you can have graphs where edges are order n. Then you need a more realistic estimate of the complexity. That is where we generally keep uh, m and n terms separate.
Sir?
Yes.
Sir, we are also storing the tail of each linked list, right?
Yeah. That you have to update order one time. Yeah. Each union you will have to update the tail. Each union you have to update size.
I mean, where that field will go, like, where will we store that? Within the node structure only?
No. Separately you are storing three things, right? Head, tail, and size.
Oh, okay.
So we are storing the tail of linked list, right, in each node. So when we update, is it not necessary to change?
We stop worrying about nodes that are no more the head of a linked list. Okay. Even if they have an older tail, doesn't matter. Because we will never use that. We will never use their tail. We will use tail only for a node that has a linked list. And that tail we are updating. So here you will update, suppose you put this linked list at the this at the tail of this. So you will update the tail of this linked list. You don't worry about this anymore. You only update the tail for this linked list here. That's all. You update the size of this linked list. Does that answer? All these are order n. So this is my complexity with the linked list. Okay. Now one more thing I will say. So this analysis we did, this complexity analysis we did. So this is called amortized analysis. What is the idea? That you see what may happen in the worst case was order n. In the worst case, you were finding complexity is order n. But when you did an average analysis, you took all the operations you will do and an average over all the operations. So where you do an average over all operations. And then you find out, okay, for each node only order log n. Only order log n is the amortized complexity for back pointer update. Okay, so this was not directly using the worst case. Worst case argument would have given us order n square. But now we found out the whole sequence. So this is what will happen, this will happen. So now from this analysis overall, I'll only update log n time. Okay, so this particular analysis is called amortized analysis of complexity. We don't do that too much in this course, but just so that you know, this is a term, amortized complexity analysis, and we did it once in the case of linked list.
Sir, we are doing it O log n time, but every time, how much is the time complexity? Am I audible?
Yeah, I can hear you. Complexity for what? Complexity for each back pointer update is order one.
No, sir, for the size update also.
For the size update, order one.
No, but we have to update size for all the nodes.
The size you update only once when you do union, right?
So, sir, we need to update the size of each
You
of
need to
these.
update the size and tail only for this node, only for this head node of the linked list. That's all.
So why we are storing that head and tail for all 0 to n minus 1?
You store that because initially you do not know which nodes will end up being the head of the linked list, right? So you just store for all, and later on you use only for some. Others are there. How does it matter? They will remain there. You are still using order and storage. Yeah, tell me.
While combining these the smaller linked list to the bigger linked list, we are changing the tail of the bigger linked list and head
Correct.
of the smaller linked list. So sir, the net means
No,
the
no,
total
no.
number.
We are not changing the head of the smaller linked list. We are just changing this next pointer. This will point to this node. Okay. I'm not going and changing its head pointer. This still has the same address. This still has the same address. I'm just changing this next pointer. I'm changing back pointers.
Yes, sir.
Okay. Then
Sir, for
I'm
changing back pointers also.
Then I'm changing the size. Okay. Then I'm changing the size once, and I'm changing the tail once in each union.
Sir, can't we forget the head pointer of the smaller linked list?
You can free that if you want, but you need an address, right? You need an address to each node still. So you're just having that storage. Of course, the tails may not be needed later. The tails may not be needed. You can free if you want, but yeah, we only and things.
Sir?
Yeah.
Sir, is there a centralized data structure exist? I mean, we are only changing the values on the central node, and all the other nodes that are related to it gets affected.
What is the centralized data structure? We are only having this this array of struct where you are storing three things, and you know when to change what. This does not change, right? And everywhere, all of these are at their addresses, and you keep on doing some changes as per your algorithm. I don't know what you mean by a centralized data structure.
Sir, I mean that in this case you are changing all the values of like back pointers to the head node, right?
Yes, I'm doing that. Yeah.
Sir, I mean to say that is there anything exist that without changing these pointers, I mean there is pre-assumed a head node, whosoever is linking that thing, and whenever we change the head node, every other elements gets affected.
Oh, I don't know that. Maybe there is something like that. I'm not aware of something that can do this reactive thing. That once you do this, automatically this changes. Yeah, maybe there is some way you can do that, but not here. Okay, I'll pass this
Sir,
question.
come to the page where you did that analysis of means log n times. Here, sir, whenever you do it 2 to the power, now whenever the size of the set becomes 2 to the power I, we did a means we did updates 2 to the power I minus 1 times. So when you count total number of updates, that way it becomes n square. Means when we did when the size of the set became 2, we did update 1 time. When it became 4, we did update 2 times.
No, you are seeing the wrong logic. You are seeing the wrong logic. You are seeing, oh, when the size become 2, I have done update at least 1 time. No, I was doing the other way around. When you have done update once, the size is at least 2. Other way around is not true. Other way around is not true. Okay.
So when we have updated thrice, shouldn't it be 6 minimum size of the list?
Really?
So I mean, we are going from basically the smaller linked list is being updated again and again, right, sir?
Also, sir, there is a possibility that this cannot always be the smaller linked list. After some updations, this will become longer. I mean, the remaining elements
Then
cannot
you
be.
will not update its back pointer, no? You are never updating the back pointers of the longer linked list. They remain the same.
Okay.
Right? So you have, think about a node. What is the problem in the argument? First time you are updating the back pointer, you update back pointer only if it was part of a smaller linked list. So after you update its back pointer first time, what is the size of the linked list in which it will reside? It will be at least 2, right? Now I'm saying, oh, when I will update its back pointer second time, that means its back pointer has already been updated once. Its size is at least 2 in the linked list. If I'm updating it again, that means it is part of a linked list that is of size at least 2, and that is a smaller linked list. So overall will become 4. Now it is already a part of a linked list at least 4 size. You are
Sir,
updating it
we have to update the back pointers of all the nodes which are similar to this.
Yes, you can repeat this argument for all the nodes. I'm just saying, think about one node. What is the problem with this argument?
No, sir, then it will become n square log n.
How can it be n square log n?
Because log n for one node and
For
we
each
have
node you are doing update only log n time for n nodes. How can you do n square log n time? You are just counting things like arbitrary times. If you count it here, don't count it again. I'm just counting for a node, and you can repeat this argument for all the nodes. What is the problem? I don't understand that.
Yes.
Yeah, can we move ahead from this? If somebody is not clear, right, yeah.
Sir, I only have doubt that if in the second updation we attach a node with only single element, then it will be 3. It cannot be 4.
Let's see. Okay, I'm not writing all these addresses. Linked list 1, linked list 2. Okay? You will only attach a smaller linked list to the larger linked list. You will only update back pointers of the smaller linked list. Yes? So tell me, for L1, what is it being updated first time or second time?
First time.
L1 is linked list of size 1, so its back pointer is being updated only first time. So that means whatever we said was final. So the resultant linked list will be of size 3, in which L1 is a part now. Now what this node is part of a linked list that is of size at least 2. And its back pointer has been updated only once.
Okay. Yes, sir, got it.
Okay, anyone else? Okay, right. So let's go to the third implementation. So we have order m plus n square, order n plus n log n. Can we do even better? So the third implementation is rooted trees. Okay, I'll do it slightly quickly. This we will cover also in tutorial. So the third way you can implement disjoint data structure is that you can create a rooted tree, right? Remember, this is not a binary tree, not a binary tree. Okay, and this is an inverted tree. Inverted tree. What I mean by inverted tree? Okay, so what will I do for each in make set? For each node, suppose 2, I have a parent pointer. So each node contains the ID or the value and parent pointer. That's all. So in make set, each node has a parent pointer that points to itself. So it makes it again which order 1. Now the way it is defined is in such that generally how will a rooted tree look like? General rooted tree, something like this. So you have one here, another node here, another node here. Okay, so that means the root, so ID of the set is ID of the root. ID of set is ID of root. Similarly, like in linked list, ID of that set was ID of the head node. Here ID of the set is ID of root. Okay. So that means how find will work. How will find work? Find for, what will you do in find for? You have an O1 access to this node, just like you had in the linked list case. You know the address of this node. Then you follow the parent pointers. So follow parent pointers until you find a node that has a parent pointer to itself. So you follow parent pointers until you reach the node. And how do you know you reach the root node? How do you know that you have reached the root node?
The parent
The
point
parent will be itself.
Parent point to itself. Okay, so find is this. Now what will happen in union? So union. So this is fine. Now what will happen in union? So suppose I have this tree and let me write another tree. 2, 3, 6, 9. Okay, so I have 2 trees. I want to do a union. What can I do? What can you
Sir,
do?
it is one tree, right?
It is?
It is one tree only.
No, there are 2 trees. There are 2 trees. This is one tree. See, in this set, each tree corresponds to a set. Each tree corresponds to a set. Initially, we had as many trees as the number of nodes. So each node is root, and that is pointing to its parent pointer is pointing to itself. Now, in general, at some point of time, you will have suppose 2 sets. One set has 1, 4, 7. Another has 2, 3, 6, 9. Right? And they have their own root elements. I'm saying now you want to do a union of these two to create a single tree out of this. So what can you do?
Sir, I will create a parent of 1 and 2.
What is the parent of 1 and 2?
So change the parent of 2 to 4.
Yeah, so okay. So now what you will do, you can do 2 things. One is I can change this parent pointer from here so that it points to 1. Or I can change this parent pointer to point to 2. That's all. Only one of these, not both, right? Yeah.
So like this tree won't have maximum two means 2 subroots. It could have more than 2 subroots.
Remember I said this is not a binary tree. This is not a binary tree, right?
It's a tree, okay, sir.
It's a rooted tree, not a binary tree. And that is why we don't have left, right. We are only having a parent pointer. Right? Parent pointer is fine. So you can do either of this. Let me just keep one of this so that it becomes easy to see. Okay. So like something like you will put the parent pointer of 2 to the parent pointer of to the root of 1. Okay. So parent pointer of the root of set A or tree A is set to the root of set B. That's all you do in union. So what is the complexity of union? Huh?
Order 1.
Order 1. Oh,
Order
so
of 1.
we never saw. We never saw union being order 1. And we have a data structure of disjoint set where union is order 1.
Sir,
What have we compromised on? What have we compromised on?
Find.
Complexity of find.
What is the complexity of find?
order.
Order?
N.
Yes,
N.
sir. Order n.
This will be the height of the tree because I have to keep on traversing the parent pointer to go to the root. So this will be the order h. And what is order h?
Order n.
That is order n. So have we gained anything? What is the complexity? Order.
Sir, how is
n.
union order 1? Because we need to find anyway. So what, the complexity of union should be the same as the complexity of find.
Very good question. You see, the answer is that in the particular way we are doing union, when we do union xy, we only when we have ensured that what we do, we say, okay, something like a is equal to find of x, b is equal to find of y, and if a not equal to b, you do union ab. Okay, so the way we are doing union, we only do union on the root elements.
Oh, okay, sir. So we guarantee that the elements are roots of the respective trees. Okay.
If you have to do arbitral union, I agree with you that I have to do 2 finds before I can do union. Okay, so here we are assuming we have done find. We already have these the roots, and I'm doing a union of these two. That's where it can be order 1. Then it is order 1. So find is already taken care of before union. So then the complexity says yes. So order mn, m finds each one having complexity n. Order mn plus n, not good. Order mn plus n is even worse. Somebody will say m is n square, so this is order n cube. Very bad. So yeah, not good. So what can we do to improve? What can we do to improve?
Connect sorted tree to the
Right, like the idea of linked list. So connect the smaller tree to larger tree always. So in this case, this is smaller. Smaller means the number of nodes. So here number of nodes are 3. Here number of nodes are 4. What I will do, that means I will not do this. I will do the other thing. I will put this pointer, this parent pointer to 2. And 2 anyway has its parent pointer to itself. So 2 is the root, and this 3 comes here. Okay. So if I do that, connect a smaller tree to larger tree always. Okay, if I always do that, very simple thing, I can show that height becomes order log n. If there are n nodes, the height of the tree is order log n. Okay, you want me to prove this?
Yes, sir.
You can prove this by induction. Okay, you can prove it by induction. So proof argument, let me give you the proof argument, and then you can see that this is very easy. So if you follow height balancing, Siddharth, I guess you've already joined.
Yes, sir.
Okay, just wait. I'm running a bit late.
Sure, sir. No problem.
If you follow height balancing for a tree of height h must have at least 2 to the power h nodes. Okay, you can prove it by induction. So what is the base case? Let's take height 1. So height 1. What is the minimum number of nodes for a tree of height 1? It should have a root and should have 1 node, right? So height 1, 2 nodes. Fine, done. Now you take the inductive step and inductive hypothesis. So then you see what will happen. You will have two trees, A and B, and suppose the heights are HA and HB. That means they have get equal to 2 to the power HA nodes, HB nodes. Okay, right? Now you see one of them will be smaller, one of them will be larger, or both will be equal. Right? Anything else can happen? Okay. So suppose A is larger than B. So if A is larger than B, so what you will do? You will put B as the as a subtree of it, right? So B becomes a subtree. Is that okay? The number of nodes will be, the height of will not change. Height remains the same.
Sir, A is larger than B in what respect? In height?
Number of nodes. Number of nodes. Then can change, right? So what is the height? Height of the resultant tree will be what? Max of height of A, height of B plus 1. Yes?
Sir, plus 1 is...
Because you already see B has a height already, and you are putting it as the
Okay, yes, sir.
Right?
Yes, sir.
That's how you are doing. So height will be max of HA and HB plus 1. Okay, and in both cases you can show. In both cases you can show. So what will happen? Suppose the answer is this. Then also it is trivial because already A had number of nodes that A had was already greater than equal to 2 to the power HA. And you are adding more nodes. So it will continue to hold. Can you see that? I want to prove number of nodes are greater than equal to 2 to the power H. So if H is equal to HA, then this is trivial because you are anyway adding more nodes. So find trivial. Second case would be the answer is HB plus 1. Then also it is trivial because 2 to the power HB. Oh, sorry. So because how many nodes are there? Now nodes are 2 to the power HA plus 2 to the power HB. And this is anyway greater than equal to 2 to the power HB. So that will become 2 to the power HB plus 1. Then also it is fine. So that's how you can prove it very simply using induction. Right. Is that okay? Anybody has a problem with this?
Sir, in this we need to consider
Tell me.
A is greater than HP.
Oh, I can't hear you very well. Can you speak louder?
Sir, in this we need to consider the fact that HA is greater than HB.
Right. All the cases are considered here. A is larger than B. That is like I have assumed A is larger than B. Even if it is equal, it will work. I mean, as long as A is not smaller. In that way, you reverse. Okay, you just interchange A and B. So this will work if A is larger than or equal to B. Without loss of generality, we can write that. A and B are arbitrary things, right? And in that case, I'm making B as a subtree of A. Here. So what will be the height? It will be max of HA or HB plus 1.
Yeah, okay, sir.
Okay. So everybody sees that?
Sir, if A is larger than B, then means how can we say that 2 power H A will be greater than 2 power HP?
What is the meaning of A is larger? A is larger means A has more number of nodes than B.
Yes, but if A is larger than B, then it does not mean that minimum number of nodes in A will be greater than minimum number of nodes in B.
Okay, got it. What you are saying. Okay. Right. So what I'm saying here, A is larger than B, right? A is larger than B. So it has some, okay, I should have written like this. So in this case, the number of nodes will be n A plus number of nodes in A plus number of nodes in B. Okay. So that will be greater than equal to 2 times number of nodes in B. And that we can say is greater than equal to 2 times H. 2 to the power HB plus 1. Okay, now it is fine. I agree.
Yes.
This is
Yes.
a better issue. Yeah, I agree with you. This is a better issue. Yeah. Thanks. Okay. Yeah. Okay, so we proved that if we always take the smaller tree as the root of the larger tree, the height remains bounded by log n. So in that case, what is the complexity of find?
Log n.
Log n. What is the overall complexity? O of m log n plus n. Pain point. In linked list, what did we get? O of n plus n log n.
Yes, sir.
Now someone will say, oh, that means trees are bad. Trees can be n square log n.
Sir? Hello?
Okay, I am back. There is some problem with the internet. Can you hear me?
Yes,
Yes,
you're
sir.
audible.
Okay. Yeah, in between I got disconnected. Yeah. Okay, can you see my screen?
Yes, sir.
Okay, right, very quickly. So now this is what we have got. So 3, or even with this height balancing, we only get this much. And with linked list, we get this. So is there something more we can do? And that is where we have a second idea apart from balance, that is called path compression. Okay, so what happens in path compression? So we say, okay, so let's take this particular scenario. Suppose this is your tree and you are doing find of 12. So what you will do, you will start from 12, you will keep on following the parent pointer, and then you will go to the root, and that is what is taking time. Yes.
Yes, sir.
And it may happen you have to do find 12 again. You have to do find for a node every time it is found in an edge. If 12 comes again in an edge, you will have to do find 12 again. Yes.
Yes,
Yes,
sir.
Yes, sir.
Can we improvise on this? So can we, okay, we say, okay, fine. I did find of 12 once. I found what is the root. Now, why do I need to keep on doing that again and again? So what I do, when I do find 12, I find the root, find root. So you know 2, okay? And then you say, okay, once you find root, in the next pass, again start from 12 and change the the parent pointer to the root directly. Wow. So then your tree becomes this. And next time you do find of 12, you get there in like one step. Very simple idea. It's called path compression. That whenever you do find, once you find the root, go back and change the parent pointer for each node on the path to the root. Okay. So that means now the analysis of this is slightly involved. Okay, I can even say beyond the scope. But when we do analysis, you can see that this actually reduces a lot. So that means if there were n by 2 nodes once in a path, all n by 2 nodes will have a O1 access to the root immediately, right? So this actually becomes very, very fast. And again, you do amortized analysis for this for complexity. It says using path compression, you get order n log star n complexity. Now, just to give an idea, what is log star n? So log star n, so log star 1 and log star 2, both are 1, base case. And for n greater than 2, not equal to, you say log star n is 1 plus log star log n. Okay, so that means what will be log star 4? 1 plus log star log 4, 2, so 2, that will be 2. What will be log star 14? That will be 1 plus log star, again inside will be 4, that will come out to be 3. Keep on doing that. Log star 60,000 comes out to be just 4. And then you go further, you can show that if n is less than equal to 2 to the power something like 65,536, that is realistically speaking, like all possible inputs you can have, log star n is less than equal to 5. Wow. So that means for like all practical purposes, this would be as if the complexity would becomes O of n plus n for all practical purposes. This becomes like a constant. Okay, so that is where trees help. Trees help in that, fine, you can do balancing, one thing, but you can also do this compression. If you do path compression, it can be shown, this becomes order n plus n, very close to that. And that is where trees are the default. Rooted trees are generally the default data structure for disjoint sets. Okay, so I did this part slightly quicker because this will be covered again in tutorial with the codes. Anything you want to ask right now before we start tutorial?
Sir, how m log star n became m plus n? Means, shouldn't there be m log star n plus n?
No. Okay, right. This became OM. This is the overall complexity for all ON find, ON make set plus OM find plus ON union. So this all that become O of n plus m.
And what is O m log star n means? What it is the complexity of each total operation for all OM finds.
No, that's what I'm saying. Using amortized analysis, what you can show for m finds, the total complexity becomes this. O of m log star n for m finds.
Sir?
Yes. So that is,
Sir,
I'm saying for all practical n, this is like 5m. It's bounded by 5m for all practical n's. That is what we said. This is like, you can agree that this is like roughly a good enough input. You won't have larger than that. Even for that, it's less than equal to 5. And think about 6. Yeah. This is again 2 to the power this. So yeah.
Sir, for updating the parent pointer.
Yes.
Sir, for updating the parent pointer, sir, we also need to traverse half of the list, right?
No, but yeah, you are doing find. Whatever you are doing in find, you are doing it twice. In find anyway, you were going from here to here once. You are just doing that part again. And again, when you are doing that time, you are changing the parent pointer. And you are done with that.
Sir, can you explain it once, please?
Which part?
Sir, this part only.
In path compression, what you are seeing, you will do whenever you are doing a find. Suppose you're doing find of 12. So you will anyway follow the parent pointers, get the root. So first thing is get the root pointer. Okay. Once you got the root pointer, then you again start from the node and take its parent pointer and make it point to the root. Again, next element, make it point to the root. Next element, make it point to the root.
Okay, sir. So which means, sir, in first step, we are just finding the parent.
The root, yes. Just finding
And
the
in
root. Then in the next step, you are just making them point to the root.
Okay, sir. Understood. Thank you, sir.
Okay, any other question on this? So this is the complexity for all of us. Roughly order n plus n. It's an approximation, and we showed why is this okay for all practical purposes.
Sir, how did we get that relation log star n equal to 1 plus log star? I didn't get.
Right. So for that, yeah, for that, yeah, I'll point you to some paper. I will point you to a paper that describes this. Okay, what I'm saying, we can do an amortized analysis for this, and this analysis gives us this complexity where what is log star n is defined recursively like this. That is what I was saying. Okay, I did not say that I explained. I proved how we came to this. I'm saying, okay, take it for granted for now that this is what happens by an analysis. Now the analysis is like much more involved. And if you want, I can share the paper that has this analysis and you can see for yourself. Okay, but I don't want to cover that in the class. That's what I'm saying. Log star is like log of. Okay, anything else? Yeah, this thing you just take for granted. I'll share a paper where you can see more details. So then I think important is the implementation part. So Siddharth, yeah, you can please.
Okay.
I have to make you the presenter. Okay, Siddharth, you are presenter now, and you should be able to share your screen.
Okay. Is my screen visible? Hello. Is my screen visible?
I can see this.
Yes, sir.
Yes, sir.
Yeah. So hi everyone, I'm Siddharth. I'm a PhD student in the Department of Computer Science, and I'll be taking a short tutorial on disjoint sets and basically continuing on from what Pawan sir has been talking about today. So we'll first briefly go over union by rank and path compression, and then we'll look at the problem statement from last year's assignment, and then we'll discuss the solution and we'll have a short discussion as well. And if time permits, I'll also execute the a model solution and show you how it works. Okay, so let's start with union by rank. So I'm guessing that you have been studying this topic today itself. So this particular slide should be very easy for you to interpret. The basic idea here is that you start off with the root nodes, each individual node, and you assign them a rank of 0. And any time that you assign a parent to any given node, you increment its rank by 1. With the caveat that the union of the two cells or the two nodes that you're joining, their ranks are already same. So for example, if 9 and 4 were being unioned here, then their initial ranks would have been, let's say, 0. And if they were being unioned with 8, let's say here, then the rank of 8 would become 1. Similarly, on the right hand side, if you see the rank of 7 is 2 and the rank of 5 would be 1, whereas the rank of 0 would be 0 and 2 would also be 0 because it's the only node there. Similarly, now when you join the two root nodes 8 and 7, when you are trying to union 5 and 3, then what happens is that the rank of 7 remains the same because it had a higher rank than 8. And the only change that you do is you change 8's parent to 7. So that's the only change that we are going to see. You are not going to update the rank unless the rank of the two root nodes are already the same. So any questions with this? We'll look at the code after we go over path compression.
Sir, can you repeat the last statement?
Yeah, so what I'm saying is that when you're joining two different, let's say trees here, let's say you're trying to do a union of 5 and 3. So 3 is in this rooted tree on the left side and 5 is on the right side. Now we are trying to do a union of 5 and 3. So what we plan to do here is we are planning to make the root of one of the trees the child of the other tree's root. So basically the idea is that you find 3, you find 5, and you see that they are not in the same, let's say, connected component. And then what you find is you find 3's parent, which is 8. And this is the root here. And 5's parent is 7, which is also the root here. So now what we are going to do is in the union operation, we are going to join these two by changing the parent of one of these nodes to the other. The best idea here is to assign the root node with the lower rank as a child of the root node with the higher rank, which means that the parent of 8 gets updated from itself to 7. So the parent pointer for 8 changes from 8 to point to 7. And the rank of 7 does not change here. Why? If you look again here, the rank of 4 stays 0, the rank of 8 stays 1, and the rank of 7 also stays 2. You can interpret it in okay, so one nice way to think about it is if you visualize this as a tree. It's not necessarily always true, but for this particular example, it will serve well. All the leaf nodes will have a height of 0. All their parents will have a height of 1, and all their parents will have a height of 2. Right? So here the rank of 7 is 2, rank of 5 and 8 are 1, and all the other nodes 9, 4, 3, 0, 6, 1, 2 are 0. So is it clear now?
Yes, sir.
Okay. Moving on to the topic of path compression. So let's say that Pawan sir gave a very nice example right now. I'll just, this example probably just generalizes what sir said. Basically, let's say you have this node X, which has its own subtree, and X's parent is U, which has its own subtree, etc., etc. And the root here is R. Once you have completed your path compression, the root node and the tree will look something like on the right side. What you are basically trying to do is some form of a balancing where you are trying to reduce the height of the tree that you have. And that is basically what path compression is about. You're compressing the path to single edges instead of having multiple paths which you have to traverse every time that you run a find operation. So once you have found X, you will update its parent to R, obviously, but you will also update every node's parent which falls on that path to R as well. So let's look at this example. Okay, so you are 0 is the root node and your X is 9, let's say. And now how do you reach from, let's say, 0 to X? Can somebody tell me what would be the nodes that you would be passing through when you go from X
0,
to
1,
the
3,
root?
6, 9.
Yeah, but in the opposite order, right? Because you're searching for 9.
From X to the root, it is opposite.
Yeah. Right. Yeah, exactly. So you will be passing through 6, through 3, through 1, and then you will reach your root as 0. Now, so these are the nodes that we have already found belong to the path, but their parents are not the root, except for one, of course, but we'll generalize it. So let's assume that we'll also update its parent as well. So can somebody tell me what will be the, what would the tree look like after the path compression has been applied?
Now 9631's parent would become 0.
Right. So 9, 6, 1's parents are already 0. And in the next step, again, 3's parent will become 0. And 1's parent will always, like the update will not have any effect. It will still stay 0.
Sir, we should also change the parent of 3.
Sorry. Yeah, of course. So the X currently points to 3. So we'll change that as well. So this is while the algorithm is in process. It's not the end step. Right. So these are the edges that have been updated, the ones in maroon or brown. And currently we are at 3. So the next step will update the parent of 3 as well. So I'll probably show you the, yeah, okay. So it's from here. Okay, so the first step, 9's parent becomes 0. Second step, 6's parent becomes 0. Next step, 3's parent becomes 0. And then finally, 1's
Excuse me,
parent.
sir, have you changed the slide?
Yeah. I've just changed the slide to show the working example.
Sir, okay, yes, sir.
Yes,
Right,
actually,
so this
there
is
is a
what the
lag.
final.
Sir.
Oh, okay. So basically, this is what. Can everybody see this slide now?
Yes, sir. Yes, sir.
Yes,
Yes.
sir.
Okay.
We can see,
So
but
this.
there's a bit lag.
Okay, I'll try to go a bit slowly then. So basically, the tree that you're seeing on your screens right now, that is the final tree that you get after your path compression has completed. And as the text here says, when you're finding the root R of the tree containing X, you change the parent pointer of all the nodes along the path to point directly to R. So 9 was our initial X. We updated its parent to 0. On the path, we also had 6, 3, and 1. So we also updated their parents to 0. Next time when you are trying to find something, let's say like 11, you would again make 11's parent to 0 as well. and 9's parent would remain 0, right? So if you effectively are searching for all the nodes here, then all of their parents would effectively become 0 in the end, and every node will be just one hop away from its parent, right? So that will mean that your search time for your find algorithm will be greatly reduced, and all paths would be just a single hop.
Sir,
Without knowing the parent, how can we change the parent of 9? We are still at 9 and we don't reach 0.
So you are at 9, but when you have reached the root, you know the root node.
So will we traverse back?
Yeah, you have to complete one traversal at least to find the root, right? Otherwise, how would you know which node to take and push to the other connected component? Basically, if let's say you had another connected component here, you would have made one of those roots parents to the point to the other node, correct? So let's go back to the, okay. If there is a lag, please let me know. I'll just explain it using this example. Okay, can everybody see the slide titled Union by Rank?
So it is completely blank. Now it is.
Yes, now it's
okay. Okay. So let's say that you have two separate trees here. One has a root of 8 and the other has a root of 7. Okay. And now you have to path compress for, let's say, finding 6. Okay. So how will you find 6? You will first find your node 6 and then you will find its parent to see whether it is in which component it is in, what is its parent. So 6's parent will be 5. Then you will again check what is 5's parent, right? You will see that 5 does not point to itself, it points to 7. So you reach 7. Then you check what 7's parent is and you see that 7 points to itself. So that is the root of this tree, correct? Hello?
Yes, sir.
Yeah, so you have the root here. Now all you need to do is you need to update every node that you have found on the path to have a parent as 7, because you know what the parent of 7 is. So you just need to go over one more time and you'll have updated the parent. Similarly for 9 here, you don't need to do anything because 9's parent is only 8 and 8 is already its own parent. So the path compression, if you run it here, the tree's shape is not going to change. Whereas for this right-hand side tree, the shape is going to change.
Sir?
Yeah.
Sir, in this method, we are not updating all of the nodes.
Correct. You are only updating the nodes which fall on the path from your find, the parameter to your find and to the root. That's it.
Okay. Okay, so if find is not being called, so we are not going to update anything.
Correct, correct.
Okay.
Because if you're not doing a find on any node, then you don't need to update wherever it belongs in that its position in the tree.
Okay.
And sir, like we have to store all the nodes that are coming on the path, no sir?
Yeah, yeah. Because you parents, so you just keep them maybe in an array or something, or yeah, you can just store the linked nodes of that those particular nodes in an array, and once you have reached your root, you update all of their parents to the root. So immediately the height or size of your tree reduces. Is there a question?
Do you store the rank of the nodes?
Yes, you also. So there are two parts to this. One is rank and the other is the path compression part. You update the rank only when the rank of the two roots that you are going to merge or you are going to union are same. Otherwise, even the rank does not get updated. So there are two things here. One is the union and other is the find. Your path compression works when you are doing your find, whereas your rank gets updated when you are doing a merge or when you are doing a union.
Rank will also change during path compression, right?
Why? Okay, yeah, sorry, yeah. So the rank of the particular root node might change, but the rank of the lower node that you had, that is not going to change, because that was, if let's say that was already a node of length 0, of rank 0, then its rank would have remained 0. If it was a node of rank 1, let's say if you had to do it path compression for 5, then its childs would not have changed, so its rank would have remained the same. But its parent's rank might be updated.
Sir, sir,
Yeah.
sir, we have to go from 6 to 7 and there is no 1 here. So sir, the rank of 5 would also change, no sir?
If there is no 1, so
Yes,
that's
sir.
what I'm saying. If you go from 6 to 7, then 5's rank might change, because 5 is 6's parent. But if you go from, let's say, 5 to 7, then 5's rank is not going to change.
Yes, sir. Yes, yes, sir. Got sir.
Yeah, so the rank can only change upwards, the up the tree, not below the level at which you start.
Sir?
Yeah.
Sir, and also if a node is not the absolute head, we are not at all interested in its rank, right?
Correct.
So even if we
But
don't...
no, but you do need, okay, so if a node is not the root, then you still need its rank, right? Otherwise, how would you add its parent's rank? And it goes down the tree in a recursive manner, right? Your rank is dependent on your child's rank.
Okay, sir. Then
Sir, if we all find 6, then the 7th rank will not change.
If you are, yeah, in this case it will not change, because 5 will still have a child 1. So 5 will still have a rank 1 and 7 will still have a rank 2. If let's say 1 was not there and you had called find from 6 with path compression, then 6 would have had its parent as 7 and 5 would have had its parent as 7, and then 7's rank would have had to change to 1 instead of 2.
So sir, we have to check the rank also from in a different loop.
While you're updating, you can check, right? If let's say something is not pointing to its parent, then you don't have to update the rank. But if let's say this particular 5 is not the parent of something, then you will be updating the rank.
Yeah, so we have to check all its child.
Yeah.
Yes. Okay.
Sir, how we will find the child? Like we are not storing the child.
Okay, I think I got confused with what question you guys were asking. Can you repeat your question?
Sir, how we will update the rank?
The rank of which particular node?
Rank of 7.
So the question is that during path compression, how will we manage the rank of all the nodes? That's the question.
Oh, okay. Sorry, I got a bit confused. So here you're not going to change the rank. I got completely confused with what you guys were saying, because you are not going to change the rank here. The rank remains same, which has been initially assigned. So okay, so let's start again. Let me try to explain it again, because I got confused and I confused you guys as well. So basically, the rank is assigned when you are creating your tree. Okay, when you are doing your make set. Okay, so let's say you had 9, you had 4, and you had 8. So when you did a union find with of 9 and 8, then 9's parent became 8, and 8's rank became 1, and 9's rank remained 0. Similarly, on the right hand side tree, if let's say you first did a union of 6 and 5, then 5's rank was 1 and 6's rank was 0. After that, when you did a union of 5 and 7, then 5's rank remained 1 and 7's rank became 2. Okay, now if you call the find on 6, okay, and you are trying to update this path using path compression, then 7's rank is still going to remain. Its rank is not going to change. Right? Is it more clear now?
Yes, sir.
So Yeah, so once you've assigned the rank, you're not going to update the ranks after path compression. You're only going to update the ranks when you do a union.
So sir, like if we take union of 4 with a tree of 8 and 9, then how will we check that we have to change rank or not?
So you know what 9's parent is. 9's parent is 8 here, let's say. Okay, let's assume the shape means that the top node is the root and the bottom node is its child. Okay, so 9's parent is 8 and you call a union on 9 and 4. Okay, so how would you do the union here? You would first find 9, whether 9 and 4, 9's parent and 4's parent, correct? So 9's parent is 8 and 4's parent is 4 itself, right? Now, what is the rank of 8? Rank of 8 is 1 and rank of 4 is 0. So by convention or by whatever strategy you want to assume, you assign 4's parent as 8. So none of these ranks are going to change. But let's say if you were doing something like, if let's say assume the right hand tree was only 0, 5, 2, there were no 6, 1. Okay. So the left hand tree was 8 and 9, 4, 3 were its children, and the right hand side tree was 7 and its children were 0, 5, 2. That's all. 6 and 1 were not present. So both the rank of 8 and 7 would have been 1. Correct? Now, if you would have done a union of 3 and 5 in that scenario, then both of their parents would have had the same rank. So you would have to update the rank of one of these parents, and you can break that tie arbitrarily. You can either choose 8 as the parent and increment its rank, or you can choose 7 as the parent and increment its rank. Either way, one of them would have become rank 2 and the other would have stayed rank 1.
So while merging two parents, if we find rank is equal, then we update one of them.
Correct.
Increment
Yes.
one of them.
Yes.
Okay.
Yes.
Thank you.
Not the parents, the root of that subtree, not an intermediate parent.
Yes.
You always join from the roots. So yeah.
Sir, let's say there was no 1 and there was only 6.
Okay.
And then we call find 6 and like we call union on 6 and 3. So we will first find 6
Okay.
and then find 3.
Okay.
Yes, sir. So while finding 6, we will update the tree on the right hand side.
Yes. You
But
will do
we
the
not
path
update-
compression updates.
Yeah, but we will
But
not
you
do
won't
the rank.
update the rank.
Yeah.
Correct.
So while
The rank
union,
of 7 will still remain 2.
yeah. So while union, will we not get the wrong answer because we have not updated.
Why will
the
you get the wrong answer? Why will you get the wrong answer?
Sir, there is no 1 there. So rank of 7 would be 1.
No, that's what I'm saying. When you are doing your path compression, you do not update the ranks.
Yes, sir. Agreed.
Yeah, so the rank of 7 would still be 2.
Okay. Yes.
So rank is not a proxy for height. I took that as an example for this particular graph that you see here. But rank is not always a proxy for height. It is a proxy for height if you are not doing path compression. But if you do not do path compression, then your trees don't change. So, okay, so let's try to look at it in a different way. When you are doing a union by rank, then the shape of your trees do not change, in the sense that the two subtrees that you're joining, they retain their initial shape. Okay. But if you do a path compression, you change the shape of that tree itself. Right? So if you look at this example, the shape of this particular tree itself has changed. Would you agree to that?
Yes, sir.
Right? So then the rank itself is not a proxy for the height. Rank does not equal height in that scenario if you use path compression. But if you do a union find without using path compression, then you can assume that your height is the same as your rank because the subtree's shape itself is not changing. And by subtree, I mean the particular component that you are joining with the other particular component. Yeah, there's a question.
Sir, we were using rank basically for balancing the tree, right? That we pick the one with a higher rank and like we join the parent to it.
Okay.
So I mean, like, what's the use of rank if we are changing the shape of the tree and we are not updating the rank? Like,
okay, so this is basically a hierarchical way of improving the complexity of this particular algorithm, right? So by union by rank by itself is not going to help you in achieving as good a complexity as union by rank plus path compression. Without path compression, what are you going to do? You have two subtrees, right? Let's say you have this subtree 8943 and this subtree rooted at 7. Now, if you are doing a union by rank, then you are explicitly joining the roots to each other. Okay. If you had not been doing union by rank, there were other ways, like a naive method where you would just join a path between 3 and 5 itself. You would make 3's parent as 5. Okay. Let's say 3's parent was 8, you would have updated 3's parent to 5 maybe. Or you would have done something else. Let's say if it was instead of union by rank, it was union by size, which means that you would have made the tree which had more nodes instead of the lower rank as the parent. Right? So there are multiple ways of solving this problem. One is more optimal than the other, but if you use path compression, then you are not going to update the rank in the sense that you use this particular rank idea to join the two roots. That's all you're going to do. Your path compression is the one which is helping you reduce the height of your tree. But rank is being used to join the two trees that you have. I guess in the interest of time, we should first look at the code and then maybe we should come back to the questions. Okay, so find set is the one which is going to do your path compression. So let's look at what the code is doing here. Okay, is the slide visible?
Yes, sir. It is visible.
Yes, sir.
Okay.
Yes, sir.
Okay, so your parameter is a node star x that you're passing, where x it's the type of your node is, let's say, the parent that it has and its rank that it has. Okay, and this is a recursive algorithm. So what you see is that you will first see if the parent of x is x or not. If the parent of x is x, then it simply means that x is a singleton node or you are already at some root and you are pointing to yourself. If it is not, then what you do is that you find the pair, again called find set on x's parent, and you assign that as x's parent. Okay, so and you keep on doing it until you reach the root. So is this particular algorithm clear? It's not very complicated to understand. You basically keep on calling find set on your parent until you reach the root. That's all this is doing. And then you finally return the root. Okay, merge set, whereas takes the two nodes. Merge set is the same as your union function. So it's just a naming thing that we are having here. You pass the two nodes x and y. Okay, and you see if x and y are the same. If they are the same, then you return 0, which means you do not need to do any merging. They are already part of the same set. If not, then you compare their ranks. Okay, if the rank of x is greater than the rank of y, then y's parent becomes x, otherwise you do the opposite. Finally, if none of these is true, which means their ranks are same, then you assign arbitrarily, we are choosing x as parent as y and we are increasing y's rank by 1. But you could also choose y's parent as x and increment x as rank by 1. Okay, so this is also a very simple idea here, what I was just talking about. Okay, so this is what your union does by rank. Okay, so now let's quickly look at the problem statement from last year. I guess this is more important and what you guys were looking forward to. So let's first read out the entire problem statement and then we look at the important parts. So there is a person called Mr. Scrooge who is a very renowned treasure hunter, and he's recently come across a map which shows a possible treasure which is buried deep inside the earth. Now this place which the map shows has m into n chambers. All right, and m and n are user defined parameters. So it has m n chambers, and there are stone walls between every 2 adjacent chambers. Also, the map contains a spell which can be used to remove these stone walls, but you are limited to using this spell only m into n minus 1 times, right? And we also know where the treasure is located. It is located just beside the last chamber. Now, Mr. Scrooge is slightly greedy. So what he does is he does not only want to find the treasure, he also wants to explore each of the chambers, since he thinks there might be some valuables in other chambers as well. Whether there are valuables or not is none of our concern. We only want to be concerned with the fact that he wants to visit each of the chambers. And he does not know which stone walls have to be removed to access each of the chambers, which means that he does not have a oracle which is telling him what the final solution should be. He has to do it on the fly. Okay. There is one more constraint, that if he cannot find the treasure within m into n minus 1 stone wall removals, the spell will lose its potential and he will be stuck and he will have to go back. We have also been told that Mr. Scrooge knows about the disjoint set data structure and he can use that to apply and solve the problem. Okay, so first let's look at the map what the map shows for the particular location of the treasure. So you see that on the top left hand side you have an open window here which you can enter, and on the bottom right hand side you see the treasure. And Mr. Scrooge has to enter from the top left side and he has to pass through all the chambers and then he has to come out on the right side. So one possible solution is like this. If you see, every chamber is possible to visit in this particular solution, right? So does anybody have any questions at this point of time about the problem statement?
Yes, sir. Could you please explain it once more?
Yeah, sure. Okay, so let's try to look at what the problem statement is trying to tell us. We know that there is some person who has to visit a map which is showing a location deep inside the earth. Now this location has m into n chambers, which means it is some sort of a grid, okay, where there are m, let's say, rows and n, let's say, columns, and that is the grid that is given to you. Now between every 2 chambers, every 2 adjacent chambers, there is a stone wall, which means there is a boundary that you have to cross to go from one chamber to another chamber. And the map also has a spell which can be used to remove the stone walls, but you have a constraint that you can use this spell only m into n minus 1 times, which means that if you, let's say, if your m is, let's say, 4 and n is also 4, you have 16 chambers, but you can use this spell only 15 times. So you can remove only 15 walls, right? You understood up till this part?
Yes, sir.
Okay. Now the next part of the question says that the location of the treasure is beside the last chamber. So you have also been told where your treasure is located. And there is one more thing that Mr. Scrooge wants to do, and that is to explore all of the chambers. So this means that there are 2 things that you have to notice here. First thing is that you have these many number of chambers and you can open only m into n minus 1 number of walls. But while doing this, you also have to ensure that all the chambers are accessible by doing this m into n minus 1 wall removals. Okay, but you do not know which of the walls you have to remove. So you have to find some random way of removing the walls, but you have to ensure that these wall removals lead you to your final treasure if it is accessible. Okay, and you have been told that you can use the disjoint set data structure or the union find data structure to solve this problem. So if you think about it, the m into n chambers form some form of a grid, and now you can try to visualize how to remove these m into n minus 1 stone walls to go from your input chamber to your output chamber. Okay, so this is the map which shows what it will look like. You enter on the top left hand side and you exit on the bottom right hand side, and this is already told to you. Okay, this is already fixed. The only thing now that you have to think about is which of the walls you have to break such that you are able to reach this particular treasure and also visit every other chamber here. Okay, so think of this as some form of a graph in which you have to remove some of the, let's say, edges. Okay, such that your graph still stays connected while you are also able to reach from one end of your graph to the other end of it. Is this a more easy way to visualize for you?
Sir, so any possible solution would be acceptable.
Yeah.
Okay, sir. Okay.
So then there's a very easy solution, isn't there? Always. Like we can just
And
go
what
row
would
by
that
So
row and then.
go down, then one right, go up, then one right. We can just do that repeatedly, right?
And will
Yes,
you
sir.
be able to visit all of the cells using that?
Sir,
all of the
we
chambers?
can.
Yes, sir.
Sir,
Yes,
we
sir.
can.
We will
Yes, sir.
do like
Do that.
mn minus 1 only.
Right. So you can do that as well, but the constraint here has been mentioned that you have to do it in a random order. Okay. So what you're saying is also a possible way, and you can maybe feed that into your random function. But the idea here is to select the walls randomly. Okay. So there are three particular constraints that we will be following. So as I said, you can first think of the chambers like a grid, and the initial and the final grid are shown in the examples here. And there is one entry point in the top left, and the treasure is beside the bottom right. Now you have to remove the stone walls following these constraints. Number one is to select them randomly. Number two is that if there are two chambers on either side of the wall which are already connected, then you should not remove that stone wall. And finally, all the chambers should be fully connected. So let's look at all the three constraints back in the figure. Okay. So here, as some of you pointed out, we could just go one bottom, one right, one bottom, one right, correct? But that is not a random way. So you'll first have to introduce randomness into your wall selection strategy. Number two is that if, let's say, there are two cells which are already connected by some path, then you should not remove a wall. So let's say this okay, sorry. Can everybody see my mouse pointer?
Yes.
Okay, so if you see, there is a straight wall between these two columns, right? And we choose not to remove this because there is already a path connecting these two from here, right? So we did not choose to remove this wall. We could have possibly removed this and not removed this. Let's say we would still have been at mn minus 1. But we cannot do this because we are constrained to not remove walls which are already connected by a path, by an existing path. Okay. Okay. So now the question statement.
Sir, didn't get this, sir.
Sorry.
Sir, sir, your last statement didn't get
Yeah,
this.
yeah. So what I'm saying is that if there are two chambers which are already connected by some path. Okay, let's look at this chamber. 1, 2, 3, 4. So on the fourth row, first column. Okay, this is chamber, let's say 4,1, and this is chamber 4,2. Okay, I'm numbering one from 1, not from 0. So this is 4,1, 4,2. Okay, you do not remove this wall if you have already removed these three walls, this vertical wall and these two horizontal walls. Okay, because these two will already be connected by a path here. Yeah.
So, sir, we are essentially stopping loops from occurring.
Correct. Exactly. You do not want to have any loops. Right. So have you guys studied Kruskal's algorithm in the class?
No, sir.
Okay, okay. So when you study that, then probably this particular problem will be more relatable for you, because the idea is fairly similar. So as one of you rightly pointed out, you do not want to have loops, as in you do not want to have multiple paths from one particular node to the other. Right. So if there is one path that has already been found from one node to the other, you will not be adding any more paths. So you will not be removing walls which are already connecting cells through some other path. So 4.1 and 4.2, the wall between them will not be removed as long as there is some other path connecting them. So it could have been from below as well. It could have been from above as well. But you would not be removing a wall which already connects to different chambers. Okay. So now we look at what. Yeah. Sorry, yeah.
Sir, I didn't get how to introduce randomness. Selecting randomly means we cannot say the computer, right? You shall choose this.
So we'll look at how you are doing the randomness, but the idea is generally to, you know how many walls you will have to remove, right? That has already been told to you. So you know the
Yes.
total number of walls that you have to remove. And now all you need to do is you need to ensure that the count is maintained while you choose a wall that has not already been removed. So what do you think you can do to remove a wall to maintain some form of an indication that a wall has been chosen or not? What can you do?
So whenever we connect some chambers, we do the union and they are in one set.
Right.
Yeah,
But that does not tell anything about the walls.
And then we will not break the walls which essentially doesn't do anything to that set. We will obviously choose walls that do that make us do unions.
Correct. But how do you know, like one of you asked that, how do you remove randomly when you do not know which walls to, like, how do you do the randomness? So I gave a hint that you can do it by choosing, let's say, maintaining an indicator whether a wall has been chosen or not, because you already know how many walls you can remove at max. That has been already given to you. That is m into n minus 1, right? So you know the maximum number of walls that you can remove, and you also know somehow which walls you have already chosen and which you haven't chosen. And after that, your union finder is going to do its work. So let's go back to the figure. 4.1 and 4.2 will have the same parent at some point of time in this computation, which is why you are not removing this wall, correct? Think of each chamber here as one of the nodes in the trees that I talked about. Okay, let's look at this from a different perspective. Maybe this particular 2D matrix is confusing you. So think of each chamber here as a node, okay, and assign whatever value you want to it, 1, 2, 3, 4, A, B, C, D, whatever. Okay. Now, each of these walls that you have are basically preventing the nodes from connecting to each other, okay, from getting into a union. All right. So if, let's say, two chambers are to be connected, what is going to happen in your union? What do you think? Can somebody tell me?
Sir, please repeat.
Okay, so assume that these chambers are the nodes of the tree that we have been looking at all this while. Okay, don't think of this as a 2D matrix. Think each chamber is a node which is isolated from all the other nodes. Are you able to visualize that?
Yes, sir.
Okay, now if two of the nodes have to be joined together or have to become part of the same component, what has to happen for that?
We have to have a path from them. Like
Correct.
one of them should be parent and the other should be child.
Correct. How do you create a path?
By removing walls.
Exactly. So now if I look at two specific cells in this figure, 4.1 and 4.2, if you see my mouse pointer, I'm hovering over those two cells, 4.1 and 4.2. You have to connect these two. Okay, let's say these are not connected. These are part of two separate components. So what are the ways of connecting them? Either you remove this particular wall between them, right? Or you already have created a path which connects from 4.1 to 4.2. Am I right?
Yes, sir.
Okay. So if you look at the right hand side figure, then you will see that there is a very straight long vertical wall here. Okay. Which is connecting these two cells, 4.1 and 4.2 here. This means that before I could remove this particular wall here, I had already found a path between these two, and they had already become part of the same component, which means once parent, both of their parents were the same or were in the same subtree, right?
Yes, sir.
Okay, so now is the idea clear of what we are trying to do here? So the better thing to do here is to try to to visualize it in a different manner, because you have been studying union find from the perspective of nodes and edges. The best thing to do is to visualize this 2D matrix also as in the form of node and edges. And then you will see that you are able to map the problem more clearly. Okay, so think of each of these chambers as a node, and if there is no wall between them, then you know that they are connected. But if there is a wall between them, then they are not connected. That's the basic idea.
Sir,
Okay, yeah.
if two nodes belong to the same set, means the same tree, then they are mutually reachable, right? That is what we will get.
Yes, yes, yeah.
Okay, sir. So means we do not take union of two elements belonging to the same set. So we do not remove a wall there.
Exactly. So you cannot do a union of two elements belonging to the same set, right? If you think about your tree examples that you have been studying till now, you have never removed and you have never done a union which results in a new tree if both of those nodes were in the same tree. So the same way, you are not going to remove a wall. Basically, if there are two nodes which are part of the same tree, you are not removing or adding any edge. They are already connected to each other. That's the point. But if they were in different connected components, then you would be removing one of the walls. Equally, you would be adding an edge to connect them.
So for each node, we go on checking like if it is connected to its neighbors or not. If not, then we do union.
Not necessarily each node connected to its neighbor. For any two nodes, you just see whether they are part of the same component or not. That's how union find works, right? Union find does not have this constraint that you have to check only with your neighbors. You choose any two. Let's say you are choosing some random wall to remove. You see the nodes adjacent to it. Okay. And then you see whether they are connected or not. How could they be connected? Either through one path or maybe directly if the wall is not present.
Okay, so I'm saying we see if a node is connected to its neighbor or not. If not, then we will obviously have to break the wall. And
Correct,
if then we do nothing.
Right, yeah. But the perspective here is from removing the walls. So the problem is that you have nodes which you need to connect, but you have to remove the walls for the nodes to be connected. So what you're saying is correct, but the perspective that you should be taking is you first find a wall and then you find the nodes around it. Okay. So maybe when we look at the solution, this part will be clear. So keep up. Yeah.
Sir, suppose we are checking two nodes.
Okay.
So at that point, how will we identify that which two nodes to check? Will it be random?
So we'll come to that. So you have already been told that you have to remove walls, right? So that is your hint that you have to choose a wall randomly, and then you have to find the nodes which are around it in some sense. So we'll see how we are going to do that. Okay. So the question also tells you the functions that you have to implement and what those functions have to do. The first function is called makeSet, which is going to initialize your data structure that you are going to work on. So initially, all your chambers are isolated from one another, which means that each chamber belongs to a singleton set. And you create an M into array C of nodes, right? So we'll look at what the structure of the node is, but you have been told that you have to create an M into N array, which means a 2D array of nodes. And you have for every node, you have to initialize its parent pointer to itself and its rank has to be 0. So we have discussed both of these things. Then you have to look at your find set function, which means that you give a node of the ijth chamber, which is its position in your 2D array, and you locate and return the root of that tree, okay, to which this particular chamber belongs. And while finding the root, you are applying path compression. So you have already been told that you have to use path compression here. And since you're using rank, you are also going to do union by rank. Finally, your merge set, which is equivalent to the union function, will take two distinct root pointers and it will assign the root based on the union by rank algorithm. Okay. Now to answer the question that so many of you have had about how we are choosing the nodes or the walls. So the question also states that you need to maintain a list of walls eligible for removal. Okay, and there are two types of walls. One is horizontal walls and the other is vertical walls. You create an m-1 into n array of array h for the horizontal walls and m into n-1 array v for the vertical walls. You also note that the outer walls don't have to be removed. So these arrays do not consider outer walls. So is everybody clear on why we take m-1 into n and m into n-1?
No, sir.
Okay, so let's look at the figure. And okay, so can somebody tell me how many horizontal walls are in this particular figure? I'll tell you the dimensions of this. This is 5 into 6.
M plus 1 into.
So 3
No, so
horizontal
tell me the
walls.
numbers. So there are 5 cells. So the size of this matrix is 5 cross 6.
4 horizontal walls and 5 vertical walls.
4 horizontal walls or 4 rows of horizontal walls?
4 rows of horizontal walls. Yes, sir.
Okay, so this is where most of you went wrong. This entire single bar is not a single horizontal wall. Okay. This small bar for which covers every cell, that counts as a single horizontal wall. So every cell has one horizontal wall. Okay. So how many horizontal walls should be there? 4 rows of how many horizontal walls?
24. 4 into 6.
Yeah, 4 into 6. m-1 into n. Right. Similarly, for vertical walls, how many internal vertical walls should be there?
25.
m-1, m into n-1.
25.
Right? Yeah, that is 5 into 6 minus 1. So now do you understand why we are taking m-1 into n and m into n-1? The first thing to notice here is that you're choosing the internal walls, right? So you have two, if there are m cells, then the number of walls covering them would be m plus 1, right? If there are m cells, the number of walls covering them would be m plus 1. Do you get that why that is true? I mean, think of your mathematics courses from your class 12th. Your permutation, right? So if you have to arrange 6 people, how many slots are there in between them? There are 4 slots in between those 5 slots in between and 2 on the either end, right?
Yes, sir.
Yeah, so the same concept applies here. You have 5. If you have 6 cells vertically, then you have 7 overall walls and you have 5 internal walls, because you are going to discard the 2 outer walls on the vertical side. Similarly, you are going to discard the outer walls on the horizontal side. So that is why you have m-1 into h, m-1 into n for your horizontal walls and m into n-1 for your vertical walls. Now is this part clear?
Yes, sir.
Yes, sir.
Okay. Are all the function definitions here clear? Make set, find set, and merge set?
Yes, sir.
Okay.
Yes, sir.
Okay, so now let's look at what are the 3 parts of the problem that we need to solve, for which you will be marked on. So first part asks you to initialize everything. You initialize your matrix C, you initialize your H, you initialize your V, and all of these refer to the chambers, horizontal walls, and the vertical walls. You have also been told what definition to use for a node. So it's going to be a struct which has a rank as an integer, and the parent pointer is of the same type as the node. Okay, so this part should be clear, I guess, since you have already been using structures, right? The second part asks you to write a function find treasure that removes these m into n-1 stone walls such that all the chambers are in the same set, which means they are all connected to each other. And finally, you will be calling the find set to verify that your first and your final chambers are in the same set. If they are, then you print the appropriate message. Also, to visualize what you have been doing, you will be writing a function called print grid, which prints the initial and the final grid. Now this grid is printed in ASCII characters using vertical bars and dash on your keyboard, right? And you will use plus for your corners. So you have to be able to write this function as well. And the start and end chamber should have exterior openings as shown in the sample output. So you saw these, right? This particular top and this bottom right should be open. Okay. Let's look at each part separately. So how much time do I have? Hello, can somebody tell me how much time do I have left?
So we are already 20 minutes above.
Okay, so how long can you guys stay?
Sir, means complete the code.
Okay, so maybe I'll need half an hour more, so I'll request you guys to probably just delay your lunch for some time today, and apologies for that. Okay, so let's start.
So could you first show how to select the nodes? Because the remaining things are quite simple.
Okay, so let's then go at how to say. So then we'll maybe go to part 2 directly. Okay, so what does part 2 talk about? You have to write a function called find treasure that removes mn-1 stone walls. And then you call finally the find set function. So your find set, you already know it is the same find function that you have been studying, and your merge set is your union function. So the main thing that you guys want to know is how you are choosing your walls and your nodes, right? So these are the steps that we are going to follow. OK, you are first going to create a body of your find treasure functions, and then you have to iterate until your m into n minus walls have not been removed. So right. Sorry, have been removed. I did a typo here. So you have to keep on iterating until you have removed those m into n minus 1 walls. Now within this iterable loop, you are going to choose a wall randomly. By randomly, I mean literally randomly. So we'll use a random function, which is already provided in C or C++, and we are going to choose the wall from that. Once you have chosen a wall, then we will call the find set function on its neighboring chambers, and then we are going to open the wall. And then we are going to call the merge set function, and we are going to join the different cells into a single path or a single connected component. OK, so this is the signature of the find treasure function that we have in the main, which takes as input C, which is your matrix of cell chambers, H and V are the walls, M and N are the dimensions, right? Now let's look at how the main part works. So your first iterable is going to run from s equal to 1 to m into n, and it's less than m into n, which means it is going to run till m into n minus 1. Now, how are we going to choose a wall? We are just going to call a random function, and we are going to see whether it is divisible by 2 or not, the output of this. And we are going to break a horizontal wall if this is true. If not, we are going to break a vertical wall. So you understand the randomness that's working here, right? Basically, you at any point of time, you either choose a horizontal wall or you choose a vertical wall. Let's say that you choose a horizontal wall here. Then what you're going to do is you're going to find the index of the chambers that surround this wall. OK, so here what you do is you take m minus 1. OK, and you take the reciprocal of rand with m minus 1 when you divide with m minus 1. This gives you the horizontal index or the row index. The next side would be I1 plus 1, which will give you the index of the next cell, next horizontal cell. OK, and J would be the column or the vertical wall index after taking a reciprocal with n, which is the number of walls. OK, once you have both your I and J, you are going to check if that wall is open or not. If it is open, then you again go for the next iteration, which means that that wall has already been opened. If not, then you are going to continue further down. When you continue further down, you are going to do a find set on C I1 J1 and C I2 J2. And here J1 and J2 are the same. If these two are the same, then you continue. If not,
then you open the wall first. Okay.
So means if it is a horizontal wall, we'll check the
I'll show an
boxes
example.
above and below it.
Yeah, I'll show an example. Okay. So
Sir,
let's
what is
look
I1?
at this grid. Okay.
I1
Here
equal to
M,
rand.
yeah, here M is 4, N is 4, H is 12, and V is 12. Okay. 4 into 3 minus 1 and 3 into 4. Okay. This is clear. Assume it's open here instead of the top. It won't make a difference. Okay. Now let's look at what. So we've already gone through the find and the merge set. I'll directly go to the example. Let's say your I1 turns out to be 1 and your J1 turns out to be 2. So your I2 would be I1 plus 1, which is 2, and J2 would be 2. Okay. So these are the two horizontal walls that you would have found. Okay. So I1 and J1 are first used to find the walls, and from that you find your cells. So if you start indexing at, let's say, 0, so your cells would be this one and this one, right? Sorry, if you start indexing from.
Yes, sir, from 0 only.
Yeah, sorry, 0. Yeah, so these are the two cells under question. And the walls that have been highlighted in purple are the walls that you have to now check, as in the cells between these two walls is what you have to check. Okay, so these cells in blue, chambers in blue, are the ones under question. So we see that this wall is closed here. Purple here is signifying closed. So if this is closed, then we go to, as we went over the algorithm, we are going to break this horizontal wall, and now these two components are connected. Similarly, we are going to do for the vertical walls, wherein you will be checking the, let's say, left and right instead of top and bottom. Okay, so you will first find your wall, first wall, then you will find your second wall, and the cells will be the ones before that. As in, if you look at it physically, the cell would be the chamber would be just previous to the wall or above the wall. That's the basic idea here. Okay, and this is how you're choosing your chamber to break your grid. And this is what you're. Yeah.
Sir, how we are getting this one, sir, means whether it is horizontal wall or vertical wall. I didn't get that part, sir.
Okay.
You did modulo 2 part, but I didn't
Yeah.
get it.
So this is just a random way of deciding. Okay. You see if modulo 2 is true, then you decide to break a horizontal wall. If modulo 2 is false, then you decide to break a vertical wall. Okay, and you're only going to increment your S variable, your looping variable, if the two chambers have been merged. So this loop will keep on continuing as long as you are able to break walls which are joining the two chambers. It might so happen that you first break all the horizontal walls and then you go to the vertical walls, because this is a random function. So there is no user control over how which of these two parts will be chosen, whether the if block will be chosen or the else block. But you have to make a decision on either to go for the horizontal block or the vertical block, right? We are randomizing that by choosing modulo 2 as our function.
Yes, sir, got sir.
Sir?
Okay. Yeah.
Sir, what is the range of this random function?
The range of this random function, I think you can set with parameters, but otherwise I think this is int or double something. I'll have to check and get back to you on that.
Sir, is it greater than m-1 or less than?
It should be greater than m-1.
Yes, sir. Then it's fine.
H1 J1 will give the grid, right? Will give a grid. H1 J1 will give a box in the grid. And
Hi1 J1, right? Yeah. So yes. So this H and V also are basically two matrices which check whether these are matrices of walls basically. That's how you are maintaining an indicator of whether a wall has been opened or not.
Okay. Sir, if you boxes with no, sir, here I1 and J1 are chosen at random, right?
Yeah.
So in one case, here we find a wall with okay, sir, got it. It gives the points, right?
Yeah. So basically you get the coordinates on your 2D matrix. So once you fix your I, then you search for your J. So you're completely randomizing your process of choosing the cells and consequently your wall, whether you have to break it or not. So basically what the main problem at heart here is the union find problem, but there are a lot of layers of complexity that has been added to ensure that you are able to reach the main point, right? So these walls and these chambers are all mappable to the original problem of having cells that are initially singletons and you are joining them into a single connected component. Okay. So if you guys want to look at the other parts of the code, we could go over them. Otherwise, I guess, basically we are done. I have some suggestions for you before the assignment. Be very careful about the input and output formats in the question. And if you have any doubts, always ask. And if there are doubts which could not be answered, you make assumptions and mention them clearly. And I would prefer that all of you test the logic of each function that you're implementing before writing a new function, so that at least you get part marks for your logic that you have implemented. And try to have functions that do a single thing instead of doing many things. So for example, if you create a function called find set, ensure that you only do find set within that. You do not do any other computation there. If you have to do another computation, write another function and call it from there. It will simplify your understanding as well as mine. And always try to first ensure the correctness before moving on to the optimization. So because let's say I give you a matrix which has 100 cross 100, instead of trying to optimize this 100 cross 100 grid, first ensure that it works on 10 cross 10, right? So that's the suggestions that I have. If you have any further questions, we could discuss. Otherwise, I guess this is over.
Sir,
Yeah.
can you please explain that print function, sir?
This is the print grid function. So this is what your output should look like. OK. I mean, this is what your initial cell looks like, and the output would look like whatever you get after you have run your find and merge. OK, so there are a few important parts here. OK, so first thing that you do is you are going to print these two pluses, which basically are going to show the corners for these two cells. OK, because your top is going to be empty. Then you are going to run a loop for j equal to 0 to n minus 1. And you're going to print dash 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 plus. So this is going to print all your columns. OK, because you have n columns, so you're going to print it n minus 1 times because you have already printed one here. OK, so dash 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 plus 1, 1, 2, 3, 4, 5. OK, this is m is 5 and n is 6. So you print it like this. Then you run a loop for I equal to 0 to m. And you print the vertical bars. OK, which means you print the vertical bars for all the rows. OK, which means you print this vertical bar, this, 5 vertical bars. OK. Similarly, you are then going to print for j equal to 0. Now it goes to n minus 2, from 0 to n minus 2. You're going to check if the vertical wall is closed or not. If your vertical wall is closed, only then you are going to print your vertical bar. If it is not closed, then you are going to print a space, which means that your wall is open. OK.
Sir, why here
Yeah.
0 to n minus 2?
Count how many times you have to print here.
1, 2, 3. Sir, 6, no, sir.
1, 2, 3, 4, 5.
Okay.
And it goes from 0 to n minus 2. Right?
Okay,
it's less than equal to, not less than.
Yes, sir.
So the count
Like
is
we have already formed that end lines.
exactly. You have already created the end horizontal, boundary horizontal walls, right? So the vertical walls will fall in between. So your total number of iterations would be n minus 1. You will go from 0 to n minus 2. OK. Then if you have reached the end, you are going to print only spaces. Otherwise, you are going to print vertical walls again. If you have not reached m-1, then you will again print it for all the horizontal walls. If they are closed, you are going to print the horizontal walls. Where is it? Sorry, horizontal walls here, like this, right? And you will keep on doing this for all the walls that you have. So you will again print horizontal walls multiple times. Okay. So should I execute and show you one run of the program if you guys want? Or if you guys are fine with this?
Yes, sir, show once.
So one, yes, sir.
Okay, so I'm running it on code blocks, but you could run it on Linux or whatever. I'm on the Windows environment right now, so I'm running it on code blocks. Anyway, so these are the header files here, you know, hash define, you know, your struct. Then there will be functions make set, init horizontal walls, init vertical walls, the print grid function, as I said. There will be your find and merge set and your find treasure, which is going to call these functions. And this is your main. So we could either pass the parameters on the command line while we are running, or we could take it from the user. When you get your assignment on HackerRank, you will be informed appropriately, so you don't have to worry about this. And your srand here is an unsigned int. So for people who are asking what would be the type, so we are going to use this srand for our rand function, and it's basically an unsigned int. Okay. So if let's say run this, let's say we go with 5 and 6. So this is what the output looks like. This is your initial grid that is printed, and this is the final grid that is printed. Now the shape of your final grid will keep on changing based on the walls that are chosen, because we are doing it randomly. But the number of wall removals will always be constant. Right? So you should not worry about what your final grid looks like, as long as it is able to remove 29 walls and all the cells are reachable. The shape itself is not important. And you also print a label found if you have a path. So here the path is you come down, you go right, you again come down, 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 you go right, you go up, right, down, right, down, right. Okay, so that is the path that you get. And of course, there are ways to optimize your randomization, but I would leave that for you guys to figure out. And if you do not want it to keep running multiple number of times and whatever, right? So I would leave that for you guys to figure out. But and this is just one model solution that we have. So maybe if you look at the code, I'll probably just go over the horizontal and the vertical wall thing, because that is also important here. Okay, so you guys have previously assigned arrays dynamically, right? You have used malloc. Am I audible?
Yes, sir. Yes.
Okay, great. So can somebody tell me what this malloc statement is trying to do? The one that's highlighted here.
Yes, it is mallocing a 2D array.
Okay, great. And what does the internal malloc do then? Inside the folder?
Row.
Arrays, rows.
It mallocs every row.
Great. And then this hij basically assigns a value to every cell, correct?
Yes.
Okay, great. And we have already done a hash define for closed as 0 and open as 1. So this is a good programming practice. This helps you understand your own code, as well as the whoever is looking at your code is also clear. Can somebody tell me one bad thing about this code? And there are quite a few, but can somebody tell me one bad thing about this code?
No comments.
Exactly. So I would suggest whenever you write your assignment, always add comments, because it will make a good case for, let's say if you don't get marks in some particular thing, it might be because I did not understand it properly. And if you add comments, it's going to help you explain it to me if I don't assign marks, and if I don't understand, then it's going to help me understand whatever you've written. Right? So always write comments and make your keywords more verbose. Like try to write this as horizontal wall or vertical wall or something. Don't use single characters because again you'll get confused when time is short. So just a few things like that. If you have any other doubts, you could note down my email ID and drop me an email. I'm always available on email, not so much on any other medium. So I'll just share my email ID. Okay, yeah, so this is my email ID. If you guys want, you could note it down. And yeah, drop me an email if you have any other doubts. I guess we are done for the day, and sorry for overshooting by so much time.
Sir, please share the code in this presentation in Teams.
Okay, sure.
Thank you, sir.
Yes, sir.
All right.
Thank you, sir.
Bye bye, everyone.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.